imagined either as a combination of a minus and plus fictitious magnetic charge separated by a distance L, just as the electric dipole was. Or we could go to what it really is mathematically or physically, which is a little tiny current loop. And the current loops arose from the motion of the electrons around the nucleus. And in that view, the magnetic dipole produced by a current loop with a current I and an area A was the current times the area, and in a direction given by the right-hand rule. It was perpendicular to the plane of the loop, such that you curled your fingers of your right hand in the direction of the current, and that gave the direction of the dipole. So I'm just going to indicate that by a unit vector given by the right-hand rule. Okay. Now, alternatively, we could do things directly from the currents rather than going through the step of having a magnetic dipole. And if we did it directly from the currents, then the magnetic field was produced by a little current element, let's say I dl, and here is an origin. That current element was located at a position r prime, and we were finding the magnetic field that it produced at a position r. And in that case, the magnetic field produced at r by that little current element was mu0 over 4 pi, or equivalently, K magnetic, which is 1 times 10 to the minus 7, times IDL cross r minus r prime divided by r minus r cubed. In which case, to get the total magnetic field, we added up the magnetic fields due to each little current element. And so we ended up with E of r was mu0 over 4 pi times the integral IDL cross r minus r prime over r minus r prime cubed integrated over r prime.
John,
And this in turn,
I have a question.
I don't need this if I've got the DL here. Yes,
Sorry. What is R prime and R?
r prime is the vector from the origin to where the little current element is located.
Current element? And
Yeah.
So were you picking an origin?
Yeah, we pick some arbitrary origin.
Okay, and then,
This is just like Coulomb's law. Coulomb's law looked like rho dV cross, or no cross, it's just rho dV r minus r prime. And r is the vector to where you're finding the field. Okay, now, just as in the case of Coulomb's law, this combination was whatever was appropriate for the geometry. If it's a line current, it's that. If it's current on an area, it was the current per length times the area. Or if it was current spread out over a volume, it was the current density, current per area, integrated over the volume. It was whatever was appropriate to the geometry of the situation, just as we did for electricity. Okay? Then, we considered magnetic materials. And for magnetic materials, we defined a new vector, which we called H, by making the observation that if you had magnetic materials, you got an effective current due to the magnetic material, which was given by the curl of the magnetization. This corresponded to, you had an effective charge density when you had dielectric materials, which was minus the divergence of the polarization, where M was the magnetic moment per volume, just as P was the electric dipole moment per volume. So we're going along exactly the same route. Now, we showed that the differential equations for B were the divergence of B was equal to 0. That's because since it's a dipole, the lines come out one end of the dipole, go in the other. They're closed loops, so there was no net production. And therefore, the divergence was equal to 0. In the electric case, what you had was the divergence of E is equal to rho over epsilon 0. Because for electric fields, point charges produce lines. On the other hand, the curl of B was mu 0 J, whereas the curl of E was 0. Significance was that there are two possible types of lines. Lines that begin and end, those are given by the divergence. They are produced by point charges. And there are lines that are closed loops. And closed loops, they are produced, in the case of electric fields, there are none. In the case of magnetic fields, they're produced by currents. So those were the 4 differential equations that described the electric and magnetic fields. Now we're dealing with this one. Over here, when you had an electric material, what we had to do was add the effective charge that was produced by the dielectric. And so what we've done is we replaced this by rho effective, which was rho minus the divergence of P. Here, we replace J by mu 0, J effective, which was mu 0 times J plus the curl of M. All right? So what that gave us in this case was the divergence of epsilon 0 E plus P was equal to rho. And in this case, the curl of E over mu 0 minus M was equal to J. Okay? Then we let this be equal to D, and we let this be equal to H. Okay?
Are you talking about the part in parentheses here?
Yes. Part in parentheses, we call that D, we call this H. So, in this first case, the dielectric case, we said that most of the time in the dielectric case, the polarization was proportional to the electric field that produced it. Not always, but most of the time. And so we said, if the polarization was proportional to the electric field that produced it. Then what you got is D was equal to epsilon 0 E plus times of E times E, which we simply call kappa epsilon 0 times E. And that was the dielectric constant, and that's how we proceeded to solve the problems. Okay? Now, in the magnetic case, there are two possibilities, just as there were here. We might have this proportional to what produces it. But in the magnetic case, there are also many situations where it is not proportional to the field. Instead, there is a permanent dipole moment associated with the material. And those are ferroelectric materials. And so we've considered both of those cases. So, if the magnetization is proportional to H or B, could be the one, we traditionally do it as H, then what you got is that H was equal to B over mu 0 minus chi sub m times H, or in other words, H times 1 plus chi sub m was equal to B over mu 0, or B was equal to mu 0 times 1 plus chi sub m times H, which we just write as mu times H instead of mu 0. Okay, that was case 1. Now case 2 was if M is a constant. For example, it's a ferromagnetic material, all the little current loops are lined up so they make one great big magnetization. Then what happened was, from our equation, the divergence of B equals 0 became led to, since this is H, we had the divergence of H was equal to the divergence of B over mu 0 minus M. But the divergence of B is equal to 0, so this was simply minus the divergence of M. Now, you always have from our basic equation up here, we have the curl of H was equal to J. So the situation we considered was if there's no real current, so we just had bar magnets, magnetic materials, but no currents, then the curl of H was equal to 0, the divergence of H was equal to this, and that was electrostatics. Because that's the same equations we had for electrostatics. The curl of E is equal to 0, and the divergence of E was some sort of charge. And so we said we could solve problems with ferromagnetic materials just the way we did electrostatics, where you have a charge, which is the divergence of M. Making sense? Okay? So then, given that, we proceeded to work out classic situations with bar magnets. And so first we considered 2 bar magnets and asked what is the force between a pair of bar magnets. and they each have a magnetization M. It's uniform, and so the divergence of M is 0 everywhere in the magnet, except at the top and the bottom. At which point, it will simply be M at the top and the bottom, where this is M, this is M. This is the charge per area at the top, charge per area at the bottom. And so, we could find the force between the bar magnets by simply taking the force between this set of charges and this one, this set and this one, this set and this one, this set and this one. So we just added up the forces due to 4 pairs of charges. And that gave us the force between the bar magnets. And it was a messy integral, but it was just a problem of doing an integral. Okay, did that make sense to everybody? Okay, so then we considered a second problem in which we placed a magnet in contact with a ferromagnetic plate. Okay, now, since M is a constant and BH was equal to that stuff up there, that this corresponded to saying that H would be 0 inside this material, because the boundary conditions were that B had to be the same. The normal component of B had to be the same as you cross the boundaries. And therefore, whatever B was in here, B had to be the same thing in here. But here, any sort of B produces an enormous value of H. And therefore, what had to happen was that H was 0 inside. Or to put it another way, B was equal to mu times H. For a ferromagnetic material, mu is essentially infinite. Because no matter what, if you make, this has gotten as big as it can be. And that means that the value of mu is essentially infinite, because you were able to produce, you have put a trivial B and produced this magnetization. So, if mu is going to be essentially infinite for a ferromagnetic plate, and B is finite, has to be the same as it was in the bar magnet, then H has to be essentially 0. And so a ferromagnetic plate acts exactly like a conductor in electricity. Everybody understand that? Okay. So that means that we can solve this problem as though it was an electrostatic problem with charges outside of an infinite conducting plate. And we know how to do that. We did that by the method of images. And that meant that you had charges here, charges there. Those that have an image charge here, and these that have an image charge down here. The same distance. So, we solved this problem almost the same way that we solved this one. If we called this 1, this 2, this 3, and this 4, then the total force was the force of 1 on 3, the force of 1 on 4, the force of 2 on 3, and the force of 2 on 4. And this one, and this one are just the same problem we did over here. Just integrating the force between two sheets. So it's exactly the same problem we did over there. However, this one is more complicated because these things are right next to each other. And so if you do the numerical integral, it's going to be very messy because you're having to deal with the distance is very small. You got infinities to worry about because the separation between the charges goes to 0. So it is easier to do what we did when we did dielectrics, and that was to recognize that the force exerted on this charge, or therefore on this one, was 2 pi k times sigma squared directed outward. And that was because you had, by Gauss's law, you had a field here that was just given by this, but only half of it would exert a force on this, because the field lines begin on here, end on some opposite charge. Only the lines due to the opposite charge matter, and therefore we got 2 pi k instead of 4 pi k. So in our case, it'll be 2 pi times k magnetic, which is mu 0 over 4 pi, times the charge density there squared. And so we avoided having to do any of the integrals for this particular one. So we added up all 4 of them, and we were able to predict the force that you were going to get on that would take to remove that bar magnet. Is everybody okay to there? So the next thing we did was to figure out what the magnetization ought to be. What is M? And we said, well, that should be easy. We know what it's due to. It's due to little current loops. So we need to know what the parameters of the current loop are. They were the current due to the electron going around the atom. And that was the charge times the number of times it goes around in a second, which is the velocity times the circumference. That gave us the dipole moment of a given loop. Then we had to know how many atoms there were per unit volume. And so we stuck all that stuff in, and we calculated that we expect for a ferromagnetic material to have something like 2 times 10 to the 6th as the magnetization. So we estimated that we would have 2 times 10 to the 6th. And the dipole is current times area, so that's amp meter squared. But this is per cubic meter, so it's amps per meter. So that's what we expect to be the magnetization M of a typical bar magnet. All right? We then could calculate the force that it ought to take to remove the magnet from the plane. And you can do all of the terms, this one on this one, all of these things. But obviously this is going to be the biggest one, because those are the two that are closest together. And so in that approximation, we do it exactly, but making that approximation, we make an estimate of what the force would be. And so it should have been this thing, 2 pi, mu 0 over 4 pi is 1 times 10 to the minus 7. M squared then is 4 times 10 to the 12th. And that's the force per area. And so then we had to multiply by the area, pi times the radius of this thing squared. And we did that, and we estimated that the force it would take to remove a bar magnet from the plane was of the order of 100 pounds. Okay, so that's where we got to last week. Was everybody following this okay? And I wrote it up on the, on the notes that I passed out. It's also online. Okay. So now today, we want to go back and solve the other case, where we have a situation where It's linear. So it's not ferromagnets. It's simply linear. And the problem we want to consider is if you have this is an illustration of how to do it. Let's do a problem exactly analogous to what we did in the dielectric case. Namely, we put a point charge above a dielectric plane. And we calculated the force that would exist on that point charge. Now, what should we use instead of a point charge for magnetism? Well, what was the analog of the point charge? It was the current loop, right? Because the current loop made the little dipoles. So what we're going to do is we're going to calculate the force on a current loop placed above a paramagnetic material. So that's something that they can mine up a little bit, but not totally. So instead of getting a large mu, semi-infinite mu, we get a mu of a few, which is the typical paramagnetic material. Okay? So, let's see how to do this. So the problem we want to consider is here you have an infinite plane of a paramagnetic material which has a value u as opposed to mu zero. And above this thing, we have a little current loop. This region is mu zero. Current loop I, and this thing it has radius r. Okay, we'd like to find the force on this loop due to the plane or vice versa. Okay? So, what would you guess the appropriate image would be? I guess we could probably solve it by images, because this is, you know that this is analogous to electrostatics. We expect that we'll need an image current, probably the same distance below the plane as the original one is above, because we have to be able to match the boundary conditions everywhere on the plane. And that's not going to work unless it's the same distance above as the other, below as the other one was above. For the same reason it wouldn't work for the dielectric case. So we guess that we'll have an image current down here, some value unknown, I prime, but looking exactly like that. And if this distance is L, we expect this distance will be L.
Will the current loop be going in the other direction?
We're going to assume they're in this direction, and then we'll get a minus sign if we guessed wrong. Now let's call this region 1, this region 2. So when we're finding the field in region 1, we expect it'll be the sum of this one and this one. We can't change anything up here because, you know, this is the reason we're considering we can't change the fundamental law, which was the curl of B is mu 0j. Well, we can do anything we want down here because this is outside our region. Same argument we did before. But when we consider region 2, we can't put anything in here because this is the region where we got to be true. But we can replace this by anything we want. So we expect in region 2 we'll have some different current I double prime. Just the same thing we did when we did the dielectric case. Okay? Now, how did we determine I prime and I double prime? We match the boundary conditions. So we need to do the same thing here. We need to match the boundary conditions.